And hi, welcome. So last time we left off, I was trying to describe how this MLS sequencer works. Okay, where was that thing? Totally forgot. Yeah, the MLS the maximum length sequence or pseudo random binary sequence. Yeah, I was trying to describe some of the inner workings behind it, and it's over here. Okay, this was my, come on, open up. Yeah, this was my what I was describing, and I was saying, okay, you kind of generate a set of signals. Okay. Oh, don't tell me this is not like working now. Okay, don't save. Alright, don't save. Let me fast forward this bit and I'll get this opened. Okay, I finally got it open. Apparently it's a little bit harder to open subsystems for some reasons. Okay. Okay, so anyway, I went through this thing called the bit generator. Okay, this is the bit generator. Okay. Let's go. Yeah. This is where I stopped the last time. So depending on the bit length that you supply and whether it's the first call, of course, then I will start generating sequences, and then you get an output based on the index array that you supply to this subsystem. Of course, the bit length you can technically change it over time. Yeah, so if I don't change it over time, then if I don't change it over time, then I want to keep using the same sequence. But if I change it over time, then I want to keep generating new sequences. So before I hop on to the part where I start indexing, I might want to just tweak this code a little bit just for convenience sake, or maybe I'll do that part later. It'll be easier to see what's going on when we start testing. Okay, so let me close this. Close this as well. Oh, bit generator index vi. Yeah. So this is what will happen now. Okay. Suppose that I only supply I don't change the bit size. Okay. How many bits this pseudo random binary sequence has? Okay. Again, bit size. Bit length. Sorry. How long is the sequence? I call it bit length. Bit size is how many seconds per bit. Okay, the 0 or 1 signal. Okay, so basically we discussed before. Okay, we discussed before that when I start running this thing, okay, maybe I'll have a bit length of 128 again. Okay, so we start from index number 0, then we go index number 1, 2, 3, 4, so on and so forth. Okay, and then we wanted, as time went on, you kind of cycle through the values in this loop. So if your bit size is 3 seconds, okay, at 0 to 3 seconds, the value will be 0. At 3 to 6 seconds, you give or take, okay, I'm not doing this accurately. 3 to 6 seconds, the value is 1. 6 to 9 seconds, value is 0. 9 to 12 seconds, value is 0. 12 to 15 seconds, value is 1. That's for a bit size of 3. Okay. So how do you get this effect? Okay. So first thing first, we will need to of course start counting the time. Okay. To count time, all right. To count time, we will need this utility called simulation time. Okay. For sure you will need a way because to count time, because how else do you know, like from 3 to 6 seconds if from 3 to 6 seconds you want to set your bit value to either 1 or 0, you need a way of telling whether it's 3 to 6 seconds. So you need this simulation time vi or the subsystem or whatever Okay, and what it's supposed to do is just tell you the time. It's nothing more than that. Okay, so it will compile and then yeah. Okay, ignore. Okay, so this is a simulation time. I can just delete that. Okay, so if I just run this VI, okay, I give it again maybe 3 seconds per bit, 128 bit length sequence. Okay, and then I just press play. Okay, so you can see the simulation time is just this VI. This is all that it's doing is just telling us this simulation time. Okay, now how do we then, what's the next step to telling us, you know, which bit are we at? Okay, which number are we at? Okay, so again from 0 to 1, 0 to 3 seconds we want the value to be 0, 3 to 6 seconds the value to be 0, 6 to 9 seconds the value to be 1, so on and so forth. Okay, how do we tell that? Okay, so okay, so the trick is this. Okay, we actually take the simulation time and you divide it by the bit size. Okay, so if your simulation time is, let's say, 10 seconds over here, as you can see, so and your bit size is 3 seconds, okay, how many bits have already passed? So you go from bit 0, okay, bit 0, bit 1, and bit 2. Okay, so that's 3 bits that have passed. So that's a total 3 bits equals to 9 seconds. Okay, so okay, so the thought process is this. Okay, first 3 seconds is bit 1. Next 3 seconds is bit 2. And so on and so forth. So this is bit 3. And you go dot dot dot. Okay, so depending on your bit size, it can be 3 seconds, it can be 5 seconds, 7 seconds, however you want it. Okay, 5 seconds. Okay, 3 seconds, 5 seconds, 7 seconds. How do you tell which bit you are in? Okay, so let's say you are at 7 seconds now. 7 seconds is somewhere over here. You should ideally be at bit number 3. Or if you want to be more accurate, you start from 0. This is bit 0. This is bit 1. And this is bit 2. Okay. So let me just delete this all away. Alright, so how then do you tell this? Okay, so your timer will tell you it's 7 seconds. Okay, your timer will tell you it's 7 seconds. Okay, how do you get, okay, if let's say this is bit number 2, right? From 6 to 9 seconds, this is supposed to return a bit number 2. This is you're supposed to get index number 2. How do you get the number 2? Okay, one simple way to get close to number 2 is actually 7 divided by 3. Okay, 7 divided by 3 is 2 and 1/3. Okay, 7 divided by 3 is 2 and 1/3. Okay, so well, the 2 is over here, so all you need to do is to round down. Okay, round down. Okay, you just need to round down this number, whatever it is, from 2 and 1/3 to 2, so that even at, like, say 8 seconds, 8 seconds, this thing becomes 8 over 3, and the number you get by dividing is 2 and 2/3. So round it down, you become 2, and this will give you the bit number. Okay. Now this is why I like to use the round down function. Okay, so I use the dividing function here. So I have my simulation time, divide by the bit size, which is what I was doing just now, and the bit size happens to be 3 seconds. Then what I do is I need to round down. Rounding down, it's this one. It says round towards minus infinity, which is basically a fancy way of saying round down. Okay, round down. Alright, so this is round towards minus infinity. That's what I'm doing here. So that's why I say rounding down. Now, all will be well and good till you reach your maximum bit size. Okay, because maybe you have 128 bits. Okay, 128 bits here. 128 bits. Let me just zoom in. Okay. Yeah, maybe it's a bit easier to write in a bigger font. maybe you have 128 bits, right? Okay, so let's say you're at 127 bits here, and things will be okay because you are at the last bit. Then for this the index number, you go from I equals to 0 to I equals 127. Okay, and 127 is the last bit. So anything lower from index number equals to 0 to index number equals 127, that's okay. Okay, so what happens if you have an index number that's 128, 129? Okay, how then do you do this? Because if you search for index number 128 in your array, it will not return anything because there's nothing there. Okay, your array is only 100 0 to 127, and index number 128, there is nothing there. 129, there's nothing there. So this thing has to somehow start from 0 again. Okay, this thing has to start from 0. 128-bit has to start from 0 because we are repeating the sequence. 129 has to be 1. Then okay, so the answer, one of the ways is that you subtract 128. Okay, one of the ways is that you subtract 128. But then if you do that, then you run into the problem when you come into the next period, which is 128 times 2. Okay, 128 times 2, you get 256. Yeah, 256. Okay, so if you reach the 256th bit, then you have to minus 128 again. So all of this will be a bit manual. Okay, how then do you deal with this in a more elegant fashion? Okay, so you might have heard of this function called the modulus. Okay, this is normally %, but it can also be it can also stand for modulus. Okay, this is not the absolute value modulus. Okay, that's not what I'm talking about here. This is more closely related to the concept of remainder. Okay, so we want a quotient and remainder kind of a thing, so that if you have 129 over 128, okay, one way of writing it is 1 remainder 1. Okay, so the remainder is 1. So you get your index number. You get your index number from the remainder. Index number from the remainder. Okay, so if you have 128 over 128, okay, this will be 1 remainder 0. So again, your index number will be gotten from the remainder. What happens if your index number is less than 128? No problem. Okay, if let's say you have 57 divided by 128, okay, you can just write it as 0 remainder 57. 0 remainder 57, so that will give you your index number. And if it's more than 128, let's say 270 or 256 over 128. Okay, this is actually just 2 remainder 0. Again, the index number, you get it from the remainder. So I've illustrated lots of cases where what I'm trying to show here is that you can use the remainder to help you find your index number regardless of how long the bits, where you are in the bits. So where do we find this remainder thing? Okay, this is a VI for remainder. You will find it under numeric, and you see this VI called quotient and remainder. So that's what you want to get. Okay, the only thing I'm really interested in is the remainder, as you saw before. And how do you get the remainder? Okay, and what you're supposed to divide? You're supposed to divide your current bit number. Which bit are we at? Okay, and you divide it by the number of bits. Okay, so you get where is it? You get your bit number, which is this rounded down number. I divide it by, okay, the number of bits, okay, or the bit length. Okay, the bit length is how long the sequence is. So that's how you get your so-called which bit are we at. That's the number. So if we were to play this again, So you can see simulation time over here, and once we are at bit number 3, okay, it's a very, yeah, you can see this thing going on and on and on. Now I don't want to make you wait 128 times 3 seconds, which is basically almost 5 minutes to demonstrate this, but I will maybe make the bit size 5 so I can show you that the looping effect works. Okay, so let's take a look. Okay, so bit size is 3 seconds per bit. Bit length is 5 bits. So you can see the sequence here is 1, 1, 0, 0, and 1. Okay, so let me close this. I'll have the simulation time sort of over here. Okay, and you can see, let me restart this. You can see that let's say from time equals 0 to 3, it's 3's bit number 3, bit number 0. At time equals 10, 11 is like bit number 3 or 4. Then okay, basically the idea is that you see this number, it will actually cycle again and again from 0 to 4. Okay, so that's actually what I'm trying to say here. Of course, I brought the pseudo-random output over here. You can see at bit number 0, the value is 0. Bit number 1, the value is 0. Bit number 2, the value is 1. Okay, then bit number 3, value is 1. Okay, long and short, the main idea I'm trying to get across here is that this algorithm is good to help us loop between the various numbers of the sequence from 0 all the way up using a bit size and a bit length. Okay, so of course if you change your bit size maybe to 1, it will loop faster. Okay, that's what we want, intended result, so it switches between the MLS sequence a lot faster. If you change the bit length, okay, ideally you want to actually have your MLS sequence regenerated. So I just changed my bit length from 5 to 2. Okay, from 5 to 2. Okay. Okay, so I just changed my bit length from 5 to 2. All right. So yeah. So this number was cycled between 0 and 1. Now I want to regenerate this MLS sequence, and what do I usually do? Okay. Well, we can actually make use again of the memory function that we had before. Okay, we use this memory function, and then we can sort of use add a condition here to this loop. Basically, it's not just at the first call that you want to regenerate. If your bit length actually changes, you also want to regenerate your maximum length sequence. Okay, you can either use this memory thing or you can use something called shift register. Okay, labview. Okay, so it's to pass data between loop iterations in labview. If you don't have the control design and simulation package, you'll probably have to use something like this. May require a little bit more manual work, but since we already have the package, we just use the memory function. The memory function is much more intuitive to use. Okay, so I'll go to utilities. I will add a memory function here. Okay, so I want to test if the previous bit length equals current bit length. Okay, so that's what this memory function is here for. I'll make it very clear. So so what do? I will wire this bit length in here. Okay, and then well, maybe I'll just say I'll call this previous bit length. All right, this is the previous this is the bit length in the previous iteration. Okay, so previous bit length. All right, so and then this thing has to have an output. Okay, where is this going? Yeah, So of course the initial value, I can just put the bit length of 0, okay, to start, okay, and then I'll put this here, previous bit length. Okay, now what do I do with this? Okay, the next step is to really compare these two, because I want to test if the previous bit length equals to the current bit length. Okay, if the previous bit length equals to the current bit length, then we don't need to actually change anything. Okay, but if it's not equal, okay, so I want to test whether they're equal. Okay, if it's not equal, okay, maybe I should use a not equal, it's better. If they are not equal, then I want to regenerate the sequence. So I'll use this non-equal tester. Under comparison, you can look for not equal. As long as they are not equal, then I want to regenerate my MLS sequence. So I can use a logical thing. I can use Boolean. Yeah, I will use the OR Boolean. Okay, so if it's the first call, or the previous bit length is not equal to the current bit length, then I will regenerate the MLS sequence. So let's put this here into this OR gate. So if either of these conditions are true, I will generate the MLS sequence. Otherwise, I will not. Okay, so I will just wire this in here. And let's see how this thing works. Okay, if it works, then we can just upload this to GitHub. Okay, hopefully, fingers crossed, it will work. Okay, so let's see here. Let's go back to the main diagram to see whether things are working correctly. So let's try again. The bit size will be 1. Okay, so I have bit length of 2. I can change to 5, and then, okay, now the bit length has been changed. So if I put 3, then the bit length will change also. So it looks like this thing is working pretty right. If I change this to 7 seconds, okay, the bit length here should not change. Yeah, so then it will start, you know, this new sequence. So this is how we can generate a time varying output for now this is a little bit long. Yeah, we can generate a time varying output using the MLS generator that it's already available in LabView. So I can change this to maybe 0.5 seconds, so it changes a lot faster. So 0, 1, 2, 3, 4. Okay, yeah, so it'll cycle through this a lot faster. Okay, so that's basically how my timed PRBS, pseudo-random binary sequence, MLS, maximum length sequence bit generator works. Okay, so now that we have this, we can actually use this to generate the signals that we want, so that we can perturb the system at multiple frequencies. Okay, so thanks for watching. I'll see you guys again next time. Bye bye.